Hi, technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything. So basically, we are going to look
Hi,
at
technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything. So basically, we are going to look Hi, at technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything. So basically, we are going to look Hi, at technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything. We are going to look at technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything. We are going to look at technical update. Yeah, so this one is going to be a very theoretical lesson. There is not going to be any language or anything.
welcome guys to competitive coding with CodeChef. If you guys can now hear me, see me, and see my screen, please drop a thumbs up in the chat section so that I know that everything is fixed on the technical aspect. Welcome guys to competitive coding with CodeChef. If you guys can now hear me, see me, and see my screen, please drop a thumbs up in the chat section so that I know that everything is fixed on the technical aspect. Welcome guys to Hey guys, if you can hear me, see me, and see my screen, please drop a thumbs up in the chat section so that I can be assured that everything is okay on the technical aspect. I'm sorry for keeping you guys waiting. We ran into some technical issues. All right, guys. So hi, welcome to my first class here on this platform. I am Rohit Mazumder. A little bit about me. I am a final year student at Jadavpur University. I am currently pursuing Bachelor's of Electrical Engineering. I was an intern at Amazon this year, and as you can see from my stream, that I'm from a non-coding background, but my love for algorithms and data structure is beyond that. And over the next couple of sessions, I'll hopefully be able to share my love for algorithms and data structures with you guys, and maybe share some bit of knowledge which I have learned over the years. All right, without much further ado, let's start with today's class. My first micro course here on Unacademy is going to be on hashing. So we are going to have three sessions. The first session is going to be today's session is going to be a very theoretical introduction to hashing. We are just going to look at what is hashing, why do we need it, how hashing is performed under the hood, what is exactly going on inside those libraries and stuff. And the next two session is going to be on problem solving, where we are going to take up various types of problems and solve them, starting from the very basic questions to moving towards more challenging ones. All right, so let's set the agenda for today. Okay, so the agenda for today is this as follows. So first we are going to look at why we need hashing. So we're going to take up a motivation problem, and we are going to instead of delving right into hashing, I want to first try and solve it using a brute force solution and slowly optimize it while moving towards hashing. Then we are going to gain a basic understanding of how hashing is implemented in the libraries, the hash functions, the hash tables, what is going on inside those libraries. And then we are going to look at some of the parameters which influences the performance of hashing. And finally we are going to look at the two most important applications of hashing, the hash set and the hash map. All right, guys. So let's look at the motivation problem. So the motivation problem is that you have been provided with a set S of numbers. You have a number set, and you have to perform three kinds of queries on this. So the first query is that you need to check whether an element X is present in this set or not. You need to add a new element to the set if it is not already present, and you need to delete an element X from this set. So you have been provided with some set, and each element of this set is distinct, and each element of this set lies within the range from 0 to 10 to the power 5. And all you need to do is we need to check whether an element X is present in this set, or if we need to add a new element to this set, or if we need to delete an element from this set. All right, so let's first try our hands with the most basic solution we can think of. So the most basic solution we can think of, let's take a set. Let's say that we have been provided with some set of numbers. So let's say that this is some set of numbers which are being provided to us. The most basic thing which you can do with this set of number is to put all of these numbers in some array. Let's say that I define an array and I put all of these numbers in that array. Now the first query asks us to check whether a number X is present in this set or not, right? We will be provided with some number, and we have to say whether that number is present in the set or not. So say for example, someone may come and ask me, hey Rohit, is there a 3 present in this set? So I'll output yes, there is a 3 present in this set. And if someone comes and asks me, hey Rohit, is there a 2 present in this set? Then I'll say that no, there is no 2 present in this set. That's all we need to do. Now guys, before we begin, one thing I would like you guys to note is that the elements provided to us have no particular ordering. Like in the question, it hasn't been mentioned that the elements are sorted like they are in an ascending order, or maybe they are in a descending order, or maybe they follow some sort of a sequence. So we haven't been provided with any such information. So the only way possible for us to search for an element in this array is to do a linear scanning. That is we start scanning from the leftmost end, and we move slowly towards the rightmost end while we check each and every element whether it's the element our target is to find that or not. So basically, if I have to check for some element X, my only way out here is to do a linear scanning. Now guys, as you might all be aware of by now, that linear scanning has a worst case time complexity of a big O of n, right? So if you do linear scanning, you're going to face the complexity of O of n. Okay, so the next query we have been asked to find is to add a new element to this set. So we have been asked to add a new element. So let's say that X is 100. So now my query is to add this 100 to this array. So how do we do that? Now guys, array is something which has a very definite length, right? So an array is something which has a very fixed length. Like whenever we are declaring an array, let's say that you are declaring an array. So how do we declare an array? We specify the length. So we say that we are declaring an array of 5 integers or 50 integers or 100 integers or a string or whatever. So we always specify the length of the array, and that is a property of an array, that the length is always fixed, and this length remains constant throughout the code. Like there is no way for you to change this length for an array. So the only way to add a new element to an array would be to create a new array. So if I have to add a new element to this array, so the size of this array is 5. So I will first create a new array which has a size of 6. Then I'm going to put all of these array elements from the previous array to the new array, and then I'm going to add the new element at the end of the array. That is the only way possible. Okay, so now we can get a little creative, and some of you may be thinking, okay, instead of an array we may be using a vector, probably a vector which is much more resizable. We may use a vector, or we may use an array list if you are a Java user, or maybe a linked list, something like that. So if we use one of these data structures, then we can add simply go and add it to the tail or add it to the end of the thing, and we won't be requiring to create a new array or a new thing. So this is basically dynamic. But if you take a look at this question, guys, it has been asked to us that we need to add an element to this set if it is not present. So my first portion would be to check whether an element is present or not. So however you are trying to solve this, as though this the first query is taking you a time complexity of O of n, whatever you do, the second query is also going to take a time complexity of O of n. And same goes for the third query. The third query asks us to delete a new element, delete an element X from this set if present. So first we have to check whether an element X is present in the set or not. So someone may come and ask me, here, Rohit, delete this 3 out from this array. So first I have to check whether this 3 is present or not. So if the 3 is present, then only we delete the thing. And how do we delete? We create another array of less size and we copy the rest of the elements. So even the delete element is going to consume a time of big O of n. So all three queries are going to consume a time of big O of n, which is very terrible. So now guys, there are few solutions using BST and linked list and stuffs like this, which may be able to optimize some of these queries. So we may be able to optimize these queries using a BST or a linked list, but we are not going to go into detail about those things. We may cover some of those in some other class. All right, guys. Okay, so now I want to explore a much more creative solution now I want to create a much more creative solution. So what we did in the first approach was that we took all the elements and we put all of them in an array, right? But now what I want to do is that instead of putting them in an array, I want to declare a large Boolean array. I want to declare a large Boolean array, right? Let's say that I have some large array out here and let's draw some. So let's say that these are the indices of my array 0, 1, 2, 3, 4, 5, 6 and goes up to something around 10 to the power 5 maybe. This is 9999, 9998 and so on. So this is a large Boolean array, and let's say that all the elements of this array are initialized with a false. That is, each and every element is a false initially. Alright guys, now what I'm going to do is that my target is to use, let's say that this array has a name, let's say this array is a, use array A to represent set S. So we are going to use this Boolean array to represent the set S given in the question. So the set S given in, let's assume a set, let's say for this purpose that the set is a 0, 4 and 6. So this is the set provided to us. So I'm going to use this Boolean array to represent this set S. So now the question is that how am I going to represent this set S using this Boolean array? So to do this, we are going to use a technique which is known as using array indices as elements. What do I mean by using array indices as an element? So I'm going to take each and every element from this set and I'm going to go to my Boolean array and I'm going to convert the corresponding Boolean value to a true. So let's take, for example, the first element is a 0. So I'm going to take this, I'm going to go over to my 0th position in the array and I'm going to turn this value and I'm going to turn this value to a true. Similarly, I'm going to do this for the rest of the element, that is a 4 and the 6. Okay, so now that I'm done with this, if you guys notice, all I have done is that I have made a of x to be true if x is present in set S. Otherwise it's a false otherwise. So since I have done this thing. Now it makes our life a lot easier. Let's say that someone now comes and asks me. Now let's see that how this Boolean array is able to solve all three of the queries. The first query was a search query. Now let's say that someone comes and asks me, "Hey Rohit, is there a 4 present in this array?" So all I'm going to do is that I'm going to go over to my Boolean array and I'm going to check the value at the number 4, and I see that it's a true. So all I'm going to do is I'm going to go and check a of 4, and I see that it's a true. So I can directly report him that yeah, there is a 4 present. Or someone may come and ask me, "Hey Rohit, is there a 2 present?" So all I'm going to do is I'm going to go to the second index. So I'm going to go and check a of 2, and I find that it's a false. So since it's a false, I can directly report to that person that no, there is no 2 present in my set. So this technique, this small technique, helps us avoid linear scanning. So no longer we no longer need a linear scanning. Linear scanning is no longer being needed. So all we need to do is just go and check values, and adding and deleting elements is the same thing. We just need to, for example, if someone comes and asks me, "Hey Rohit, can you add a 2 for me in this set?" So all I need to do is go over here and turn this into a true. Done. Or if I have to delete this 0 from this set, so all I need to do is go over here and turn this into a false. So we can just add element, delete element, and check whether an element is present or not using simple queries such as simple O of 1 queries, by just flipping elements and by checking elements. So now we have actually achieved an O of 1 per query. Okay, guys. So we're gonna take a small break out here, and let me know, guys, if you can follow up till what I've taught. Just give me a quick. Yeah, Ashutosh. Yeah, what's the max constraint for this? That's a great question. So basically, so in this question, we have been said that the elements of this set are in the range from 0 to 10 to the power 5, and so we need to represent each and every element of this set. So the set can be something like, the set may be something like 0 to 10 to the power 5. So in case I need to represent this set, I need to have all of these indices present in this array. So basically, to represent all the elements of the set, I need to have an array of range 10 to the power 5. Can we use the approach of matrix here? So I don't know what approach of matrix you're talking about. Technical update, can you give me a little bit more, uh, elaborate your question a little bit more? If the constant is bigger, yeah, if the constant is bigger, we will face a problem, and that is one of the downsides of this question. The downsides of this approach, we are going to deal with that. All right, guys, let's move on. Okay, so let's say that so we saw that how we can use a simple boolean array to represent the set, and we can perform O of 1 per query. But we obviously have a problem out here, and the problem is that, which Ashutosh pointed out, that what if the constant is big? Like what if we have a large constant, like instead of 10 to the power 5, what if we were asked that we need to take 10 to the power 18 or 10 to the power 15, something of this range, then this process is obviously going to fail, because in languages like Java, C++, or any other, most languages allows you to create an array of approximately range 10 to the power 9. If you go and create an array of range about more than this, then it's going to give you an error. So okay, so let's see what are the other downsides we can think of. So this approach may be good, but it has some downsides. Okay. Well, the first downside is actually wastage of memory. The second downside is that the approach is limited to positive integers. And the third approach, and the downside is that the large integers cannot be used. All right, so the first thing is that we are wasting a lot of memory. So since the constants are large, like we have to represent all elements from 0 to 10 to the power 5, we obviously need an array of 0 to 10 to the power 5. But let's see, I need to represent just these three elements using the set, or consider the first example. We just needed to represent 0, 4 and 6 using this boolean array, but still then we needed a large boolean array. So to represent just three elements, we still have to create an array of 10 to the power 5 size. So that is a wastage of, this is big wastage of space happening out here. So that is the first downside to us, that a lot of space is being wasted. The second downside is that this approach is limited only only to integers. Like say that if I have an array which if I have a set which has negative values or maybe decimal values like 2.5, 1.97 and so on, we cannot use this approach because the indices in an array are always integers. The indices are always integers, 0, 1, 2, 3. You cannot have an index like 0.9 or 2.5 or 1.87. So this approach is limited to positive integers. And the third approach, and the third problem is what we already discussed, is that large integers cannot be used. That is the integers which this process limited to integers up to maybe 10 to the power 9, but in case you have integers like 10 to the power 18 and 10 to the power 15 range like that, you won't be able to use this process. So these are some of the downsides to this. So what do we do now? So how do we solve these downsides? Basically the solution to all of this is hashing, is basically using hashing. So hashing. So okay guys, so hashing consists of basically two things. The first thing is known as a hash function. The first thing is known as a hash function. The second thing is known as a hash table. All right, so now the hash function, what is a hash function? A hash function is nothing but just a mathematical function, just some mathematical function, just some mathematical function, just some like f of x equals h. So here f is the hash function, f is the hash function, x is known as some key, and h is known as the, this is the h by the way, h is known as the hash code or the hash value. Hash code or a hash value. So now, and what is a hash table? A hash table is nothing but a table just like this direct. Okay, so one thing I forgot to mention guys, this technique is a very common technique. This technique is known as a direct addressing technique. This table is known as a direct addressing table. And each of these elements in the table is known as a slot. Right guys? Okay, so this is a direct addressing technique, direct addressing table and a slot. Okay, so now in case of hashing, we have something which is known as a hash table. A hash table is nothing but it is pretty similar to basically a direct addressing table. You have an array where you have a bunch of indices and you have, that's all. Basically you can say that hash table and our direct addressing table is almost similar, except the fact that a direct addressing table may consume a lot of space and a hash table doesn't do that. So now let's take a look at how hashing works in practice. Okay. So basically guys, this is a comparison of direct addressing and hashing. So direct addressing, as we saw, is that we took as some element x and we were putting it directly in some slot x. So if we go back out here, so we took an element, let's say we took the 4 and we directly put it in the slot number 4, or we took the element 6 and we directly put it in the slot number 6. But in hashing what we do is that we take an element, we pass it through some mathematical function. So we take some element and we are passing it through some mathematical function which is returning us some value, and we will put x in the slot given by that value. So here we are taking x and we are putting in slot number x, and here we are taking the x and we are putting it in slot number f of x. Is that clear, guys? Just put a quick thumbs up in the chat box if you can follow. Thank you. So let's get back. Yeah, so basically this hash, so as you can see that the difference between the two is just a mathematical function in between. So here you don't have that mathematical function, here you have an extra layer of mathematical function, and this mathematical function is magical. This mathematical function is able to tackle all of these downsides. But how does it tackle all of these downsides? Let's take a look at it using a small example. So let's take a small example. Let's say that I have been given with some set of numbers. Let's say that the numbers given to me are 0, 17, 8, 3, 9 and 100. And let's say that my hash function is f of x is x mod 11. So this is some hash function we have. Now guys, this is a typical example of a hash function. X mod some prime number is a typical example of a is a typical example of a hashing function. But this is a very simple hashing function. Like in reality, this hashing function is not used. This is a very bad hashing function. We are going to look at it into after a few more slides that why this hashing function is a typically bad example of a hashing function. And so we don't use it in practice. In practice, much more complicated functions are used. I am using this function just for the demonstration purpose so that you guys can have a look at it and understand what hashing is all about. Okay, so we will calculate all the hash values. Let's take the hash value of 0. F of 0 is a 0 mod 11, which is a 0. The next value is 17. F of 17 is 17 mod 11, which is a 6. The next value is f of 8, 8 mod 11, which is an 8. The next value is a 3, 3 mod 11, which is a 3. Next is a 9, 9 mod 11 is a 9. And the last one is a 100, 100 mod 11 is a 1. So now we have all the hash values. Now we need to draw the hash table. So now let's take a look at the picture once more. So this is the picture given to us, right? So now you can see that the element x goes in the slot given by f of x. Now if you can look at this function for a moment, let's take a look at this function for a moment. This function is what this function is doing, it's taking a number x, it's dividing it by 11, and it's just returning me the integer. Now if you guys can recall from basic mathematics that if you have any number x and you divide it by n, the remainder is always in the range from 0 to n minus 1. So this is very basic mathematics. I'm not going to go into details with the proof and everything. So this is a very basic mathematics that if you have a number and you divide it by some other number, you get a remainder between 0 and that number minus 1. So that is if you divide x by 11, the number is always going to be in the range of, this answer is always going to be in the range of 0 to 10. So in case I am having a hash table where I'm putting values, where I'm putting x and in correspondence to f of x, then the hash table must have only slots from 0 to 10. Since the answer is always between 0 to 10, the number of slots is going to be 11, and we will have to put values from 0 to 10. So let's draw the hash table now. Okay, so let's put the indices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Alright, so now what we are going to do, we are going to put all of this set, the elements from the set to our hash table based on their hash value. So the element 0, the value 0 goes in the slot number 0, so we put it here. The next value is a 17, the hash value is a 6, goes out here. The next is an 8, it goes out to 8. So 3 goes to 3. The next value is a 9, goes to 9. And the 100 mod 11 is a 1, so 100 goes out here. So this is basically how hashing is working in practice. Now if we are asked to find, let's say that someone comes and asks me, hey Rohit, is there 100? So someone comes and asks me, hey, check Rohit, check please can you check me that there is 100 or not. So what I'm going to do is I'm going to take the 100 and I'm going to calculate the hash value. So I'm going to take 100 and I'm going to mod it with 11 and I see 1. So I'm going to go to slot number 1 and I see the value there. So if I see the value is 100, then I can directly report to him, yeah, it's present. Now let's say that someone comes and asks me, hey Rohit, is there 200 present in this array? So there is a 200. So I'm going to calculate the hash value, which is 200 mod 11, which is a 2. So I'm going to come to the second slot, the slot number 2, and I see that it's an empty. There's an empty space. There is nothing present. So I can directly report to him that yeah, so there is no element of, there is no 200 present in my set. So that is how we can use this hashing thing to basically reduce the size and do. We are still performing each query at a O of 1. We are adding, when we are adding element, we only have to calculate this function. This calculation of this function is taking O of 1 at mask. We just have to find the remainder, and after we find the remainder, we just have to put the element. So the calculation of adding an element or deleting an element or searching for an element still remains at O of 1. So the query still remains at O of 1. Now let's see that how this function is actually tackling all the downsides. The first downside was that the previous approach was consuming a lot of space, right? So the previous approach was consuming a lot of space. So as we can see from here that the space, that problem is gone. We'll no longer need a lot of space. Like for example, if I have to solve this using the direct addressing technique, so someone comes and asks me, you have to solve this using direct addressing technique only. So then I need to create a direct addressing table, and the indices need to be at least 0 and at most 100. So I need at least 100 places to put this place, but put these things. But in case of a hash table, I just need places from 0 to 10. So from direct addressing, it will required 0 to 100, and for a hash table we just need from 0 to 10. So we have obviously solved this memory problem. So the next problem is that the previous approach was limited only to positive integers. Like we couldn't use any decimal numbers, we couldn't use any strings. Let's say we had in some strings a b or some a b c, ABC and stuff like this, and someone asked us to perform the same exact queries. We won't be able to do them because an array index is always a positive integer. We cannot have any other data type there. So that is the reason why this approach was only limited to positive integers. But in case of hashing, if you take a look at this diagram, this function is basically providing an abstraction, guys. It's basically providing an abstraction between the elements on one side and the table on the other side. It's so even if I have some strings, let's say this x can be a string, can be some decimal numbers, or can be negative numbers, can be large integers. So whatever it may be a string, it may be a decimal, it may be a negative number, it may be a large integer. As long as I can write a proper hash function which converts this x to an integer, we can use this approach. What I mean by converting it to an integer is that I have to do some mathematics on it and convert it into an integer. So for a string, maybe you have some string like this a, b. So maybe we can take out the ASCII characters of each string, multiply it with some prime numbers, and ultimately code it to some, like convert this string to some integer. Or maybe for a decimal number, we may have some complicated mathematics. We can figure that out maybe some other time. Or maybe in negatives, similarly, we can have some complicated mathematics which may convert this entire x to an integer. So if we can do that, if we can write a proper hashing function which converts a string or a decimal or negative or a large integer to a integer or low range integer we will be able to use this method. So basically with hashing we are able to solve all three of these problems. Alright guys, we will take another break now. Guys, if you can follow up till now, just drop a thumbs up. Or if you have any other any question up till now, feel free to ask. All right. Okay, guys. So now, even though we have solved all of the problems associated so far, we still have a few downsides to this approach. And the downside, let's look at the downside up for a bit. Okay, so let's say that given this, we have this situation, we have these elements, and we have to hash the elements. We are hashing as usual. Now let's say that we have a query where we need to add a new element. So let's say that I need to add an element, and that element is a 25. So what I'm going to do, the step one would be calculate f of 25, which is 25 mod 11, which is a 3. So next step would be coming to slot number 3. So I come to slot number 3 and I find that it's already filled. What do I do now? What do I do now? Like, how do I process this information? Like, I'm trying to put 25 in slot number 3, but it's already filled with some other number. So this is a very common downside which we face while we are using hashing, and this downside is known as collision. So when two or more elements produce the same hash, it's known as a collision. So now we need some way to handle this collision. So when two or more elements are producing the same hash, it's known as a collision. So guys, a side note, a collision is a very basic thing which is used in hacking. So like all the hackers, they always try to provide collisions to bring down system. So anyways, so collision, so when two or more elements produce the same hash, it's known as collision. So how do we prevent collisions? So how do we handle collisions? Okay, before I proceed, I want you guys to, I just wanted to ask you guys, are you guys aware of linked lists? Just drop a quick yes or no or a thumbs up if you guys are aware of linked list. So we don't need to a very in-depth understanding of linked list. Just knowing the basics and the structure is going to be enough. So let's take an example to understand slotting. Sorry, chaining. Let's say that I have the elements, following elements with me. 1, sorry, 1, 12, 4, 60, 15, 48. So these are some elements provided to me and I need to hash them. So let's assume some hashing function. Again, let's assume some hashing function. I'm going to take the same hashing function for convenience. All right, so x mod 11, I'm going to take the same hashing function as last time. Let's draw the hash table, guys. So this is 0, 1, 2, 3, 4, 5, 6, 7. All right. Now let's calculate the hash values. First, let's calculate f of 1, which is 1 mod 11, which is, sorry, 1 mod 11, which is 1. Let's put the 1 out here. The next hash value is 12, f of 12, which is 12 mod 11, which is 1. So here we have a collision, guys. Two or more elements are having the same hash. So you can see the for corresponding to 1 we have 1, and corresponding to 12 we have a 1. So two or more elements are having the same hash, and hence here we have a collision. So what do we do now? So now in case now what we're going to do in chaining, so this process is known as chaining, by the way. So what we are discussing is known as chaining. So in chaining, what we do is that we assume that each of this slot is a linked list. So there is a linked list here, there is a linked list here, there is a linked list here. So instead of just considering them to be a plain random array where we can just put elements, we consider this to be an array of linked lists. That is, each index is representing some linked list. So what I'm going to do, that whenever we have a collision, instead of placing values in an array, I'm just going to add that as a linked list node. So we have this 12, we are putting the collision, we have a collision at 1. So instead of putting the 12 here, we are going to add a linked list node, and we're going to add it to the end of this. Similarly, let's do it for the next element. The next element is a 4, and the more hash value of 4 is a 4, so we just put it here. The next value is a 60, the hash value is 5, so we just put it here. The next value is a 15, the 15 mod 11 is a 4, so we have a collision, so we just add another new linked list node out here. Alright, the next element is a 48. We are calculating the hash value. The hash value is again 4, so we add another linked list node out here. So basically that's how we can resolve collision, guys, using chaining. So this process is known as chaining. So where whenever you get a collision, you just keep on adding. We just maintain a tail pointer. We are always maintaining a tail pointer. So whenever you have a collision, maybe let's say that you want to add another element 70 to this. So 70 mod 11. So f of 70 is a 70 mod 11, which is again a 4. So you're going to come over here 4, and you're going to add this 70 to the tail pointer, and move the tail pointer to here. All right. So this is basically how we can handle collision using chaining, but chaining has a very big limitation, you can say. It's a very big disadvantage or a downside, and that is that chaining increases your search time. Like for example, let's say that I want to search for the 70. So what is going to be my first step? My first step is going to be calculating the hash value. So I calculate the hash value, and I find that it's a 4. So I come to the 4th slot, and now I find a huge linked list out here. So now I have to check whether the 70 is present or not in this entire linked list. Now how do I do so? So the only way out for doing is to do a linear scanning. See, since this linked list has no ordering whatsoever, so the only way to do this is to just keep checking from the start till the end if I have this 70 or not. So so this chaining is increasing my search time. Previously it was just a matter of calculating a hash value, or just a matter of checking some value in an array in a direct addressing technique. But in case we are using chaining, we have to first calculate the slot value, then we have to come to the slot, and we have to then check whether or not the particular element is present anywhere in this entire linked list or not. So chaining increases search time. Okay, now let's do a quick complexity analysis of everything which we have learned so far. Okay, before moving on to the complexity analysis, let's draw a quick conclusion. The conclusion was that chaining increases search time. So this conclusion rather forces us to think about one more thing, that is the selection of a good hashing function is very important. Like chaining increases search time, and so this conclusion brings us to another conclusion, and that is selection of proper hash function is very important. So what do I mean by a proper hash function? What do I mean by this? What do I mean is that a good hash function, a proper hash function, or basically proper hash function is one which distributes the keys among all slots of the table uniformly. So a good hash function is one which will distribute which will take all of the keys and it will put them in the slots such that the distribution is a very uniform distribution. So take for example that let's say that you have a hash table and the number of slots in the hash table is, for example, 10. Okay, and let's say that the number of elements you want to hash is 20. Okay, so you have a hash table and there are 10 places to put the elements in, and the number of elements which you want to put in is 20. So a proper hash function is one which is going to distribute this 20 elements evenly among the 10 slots. That is, after hashing is done, if your hash function is good, then you are going to have 2 element per slot. You're going to have exactly 2 element per slot. So this is a very ideal scenario. This is a very ideal scenario. Like if you get a very good hash function, if you discover a very good hash function, the selection of a hash function is a very active research area. The computer scientists and statisticians and mathematicians are coming up with more and more better hash function to use, which provides us with this uniform nature and several other things. So basically, if you find a very good hash function and that is going to distribute your elements uniformly, then each slot is going to have at most 2 elements. Alright guys, so that is a good hash function. And if your hash, so from this now you can, now if we look at this figure, now you will find that this function out here is not a good hash function. Why? Because most of the slots are empty and one of the slots is highly piled up. So this slot is highly piled up, like this slot has 4 elements, but majority of the slots are empty. So the distribution is non-uniform, and if the distribution is non-uniform, then we suffer from the consequence that the linear scanning is going to take a long time. Like for example, in this case, if this pile gets linked list keeps on getting bigger and bigger, the linear scanning time is also going to increase, and ultimately we are going to end up with a worst case time complexity of O of n. So which wouldn't be any better than the first process which we learned. So the first process had a linear scanning and time complexity of O of n. So in this case, if we have a proper hash function, things are going to get piled on and we are going to have a very bad performance basically. That being said, let's now do a quick complexity analysis of whatever we have done so far. Let's assume for now, that we have an extremely good hash function. We have an extremely good hash function which will be able to distribute everything uniformly. So if that's the case, then searching time, let's take a look at the search time. So for searching, first we need to calculate the hash value, and then we need to search in the linked list. So that's what we need to do. First we are going to take some value x and we are going to calculate the hash value, and using that hash value we are going to go to that slot, and then we are going to search in the entire linked list present in that slot. So the first step is going to this thing is going to take an O of 1, obviously. We need O of 1 time to calculate the mathematical function, and next is searching in the linked list. Now let's suppose that the number of slots in my table is m, and the number of elements which I want to hash is n. So if I have a very good function, very good hashing function, then the number of elements per slot is going to be n by m. So to search in the linked list, we are going to require a time of n by m. So so the total complexity in my case, in this case, is going to be n by m. So 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 we can say that a hash table with chaining takes an average. Now we are using the term average. Why? Because we had assumed initially that the hash function is extremely good, but in real life it's not so good that everything will be distributed uniformly, so there will be some ups and downs. So in average case, the time complexity is going to be with chaining takes an average for searching, adding and deleting. Alright, so let's take a pause again and let me know if you can follow so far. If you have any questions, just post them in the comment section, and if you don't have any question, just post a thumbs up. Yeah, in STL, Ashutosh is asking, in STL what kind of hash function is used in backend. Yeah, so this is a very good question. In STL or in Java, there is the hash function which we use is extremely complicated. So I'm not going to go into detail about those. You can just check the documentation. They have over there a small section which they have discussed, and you can even check some Stack Overflow links also. It's a very complicated hash function which they are using these days. First, they convert the entire thing into a fixed size hash, and then they do a second hashing, so there is a double hashing involved. Yeah, so let's proceed now. Okay, so let's come to the next section. And the next section is known as the performance parameters, basically. So we are going to now talk about some parameters which influences the performance of a hash table. Okay, so we are going to start from the complexity analysis. All right, so we have now analyzed the complexity. The complexity is O of 1 plus n by m for every searching, adding or deletion queries. Now that being said, this term n by m is known as the load factor. And this is a very crucial parameter, very crucial. Crucial parameter for hash table. Why is this a crucial parameter? Let's understand with an example. Let's say that the number of slots is 100, and let's say that the number of elements we want to hash is 10 to the power 5. That is, now we have 10 to the power 5 by 100, which is 10 to the power 3 elements per slot. Alright, so now let's say that we have 10 to the power 3 elements per slot. So so let's say then this is in the best case when we have a very good hash function. So if we have a very good hash function, we are going to have 10 to the power 3 elements per slot. Even if the hash function is very good, this number is a very high number, guys. This number is a very high number. So we, even for a very good hash function, the search time may take a large amount of time. Searching may take a large amount of time. Like, you need to first figure out the complex. First you need to figure out the hash value, which just takes O of 1. But the next portion is a 10 to the power 3. So this section is a 10 to the power 3. So it's going to take a long time to just keep on searching through that linked list. So as our load factor is also denoted by alpha. So as our load factor increases, our performance decreases. So that's the deal with load factors. So even if we have a very good hash function, but you keep on adding elements, your load factor is bound to rise, because then if this number of elements you are keeping on adding is increasing, so the number of elements is increasing, so the number of elements per slot is going to increase, so the performance is going to decrease, because it will take a long time to search the entire linked list. So now what do we do now? So how do we solve this? Because we have to keep adding elements. We cannot enforce the user. We cannot tell them, okay, now you need to stop adding elements so much because it's going to hurt the performance. That's not going to be the case. So how do we handle this performance issue with rising load factors? The only way you need to handle is to reduce. We need to reduce this load factor somehow. So we need to reduce the load factor somehow. So the way we reduce the load factor is known as rehashing. The technique is known as rehashing. So here are some steps regarding rehashing. So what happens in rehashing is that first we set some cutoff load factor. So we say that we have some load factor and some initial size of the table. So we begin with a table which has some initial size. So by size I mean the number of slots. So that may be initially there may be 100 slots or 200 slots present, and we set some cutoff load factor. Now we keep adding elements to our hash table as usual. You keep adding elements to our hash table. As soon as my load factor crosses the cutoff, I am going to create a new table with twice the size as initial size. Next, what we are going to do is that we are going to discard the old table and rehash every element into this new table. Now let's take an example to understand this better. Let's say that I fix my cutoff. Let's say that I fix my cutoff at 2.0, and let's say that my initial size is 100. That is, initially we have 100 slots in my hash table. Now let's say that I keep on adding elements. Now we come to step number 2. We keep adding elements. So since we are adding elements, let's say that we keep adding elements till we reach 200 elements. Till 200 elements, it's not a problem. Till 200 elements, the load factor is less than or equal to 2.0, right? Because 200 by 100 is a 2. So till we are so we keep adding elements until the number of elements are less than 200, less than or equal to 200. My load factor is less than 2.0. But as soon as I add the 201th element, as soon as I add this, my load factor is going to cross this cutoff. So we are going to cross the cutoff. My load factor is going to cross the cutoff. So what we are going to do now is we are going to discard this old table and we are going to create a new table. So we create a new table with size of 200. We create a new table with size 200, and now we take each and every element from the old table and rehash them and put them in the new table. So we take each and every element, we pick up one element, we hash it and we put it in the new table. We take another element, we hash it and we put it in the new table. So this is what we do. So after doing this, you can notice that my alpha is going to fall again. So my performance is going to increase. So that is what rehashing is all about. So whenever so we keep adding elements again and again. After some time, my alpha is going to cross, and my cutoff alpha is going to I'm going to cross my cutoff alpha, and then I'm going to have to replace with a new table, and again I have to do this entire thing all over again. So this is an iterative process. So I have to keep doing this. So now rehashing comes with a downside also. So there is also a rehashing downside to the rehashing technique, and that is the rehashing takes a complexity of O of n, and this cannot be reduced in any way because you have to pick each and every element. Like this step takes the most. So this step is easy. So this is just an O of 1 process. This is some process. So this is also an O of 1 process, but this last step is going to take an O of n process, because you have to pick each and every element from the previous array and put them into the new array, to put them into the new hash table. So however you try to do this, it's going to take a time complexity of O of n. So you cannot reduce this. But good news for us is that this is basically some occasional. So this is an occasional. So that is, we don't encounter this a lot. Rehashing, we don't encounter rehashing a lot. Like for example, if you are hashing 1,000 elements, maybe you will encounter rehashing thing maybe 5 to 6 times at max. So for adding 1,000 elements, we are just having 5 to 6 times this O of n thing. Rest of the thing is just an average complexity of O of 0, O of 1 plus n by m. So the average complexity is still low. Alright guys, so have you been able to follow so far? Just put a thumbs up, or if you have any questions, just post them. Alright, okay, so let's now take a look at the summary of whatever we have learned so far. So this is a small recapitulation from this section. So the first thing is that hashing helps us to get searching, addition and removal. Okay, so before I go into this step, let's talk a little bit about the good parameters, the good values of performance parameters. Okay, so guys, the rehashing is a very simple technique. So as you saw, it's a very simple technique, but the tricky portion is this one, selecting the cutoff load factor. We have to select a cutoff load factor. For example, in this example, we have chosen the cutoff to be 2.0. So we are changing table when the cutoff, when my load factor is crossing 2.0. So this selection of this cutoff is very important. Like if this cutoff is very high, then it's not useful, and if this cutoff is very low, then we will be wasting a lot of space. So selection of an appropriate cutoff is very useful. And for Java, basically for Java, I am a Java programmer, so I know the values for Java. For Java, the default values are the initial size is 16, and the load factor is basically 0.75. So in Java, whenever you create a hash table or a hash map or a hash set, anything like that, its initial slice, initially it has only 16 slots, and the cutoff load factor is set to be 0.75. So as soon as 75%, this means that as soon as 75% space is consumed, Java compiler is going to throw away the old table and create a new table. So this is what, so basically from 16, then it will go to a table of size 32, and then it will go to a table of size 64, and so on. So these are some good values of some parameters. Alright, so let's do a recapitulation. So hashing helps us get searching, addition and removal of elements in an average time complexity of O of 1. So we saw that from our analysis, we saw that the time complexity is O of n plus m. So if we have the cutoff load factor around 0.75, that is less than 1, then you can see that this is basically O of 1. Right guys, since the load factor is kept pretty less than 1, this thing is going to come down to an O of 1. So basically hashing helps us get searching, addition and removal of elements in an average time complexity of O of 1 and an average space complexity of O of n for n elements. Next thing is that hashing helps us reduce the size of direct addressing table. We have seen that in detail. A good hash function is one which distributes the keys uniformly among all the slot. We have seen that too. Chaining is one of the solution to collision. Okay guys, there are several solutions to collision. We just because of the time constraint, we were able to cover just one of the things, one of the popular methods of handling collision, and that is the method which is used in most languages, but few languages use some other methods known as linear probing and double hashing and stuff. So you can find them in the documentation of those languages. Okay, to prevent long chains from forming, we use rehashing, and the load factor and the initial capacity are the two parameters which affects the performance of a hash table. The default value in Java are 0.75 and 16 respectively. So this is going to be number 6. Anyways, guys, have you been able to follow so far? Just drop a thumbs up or down. Alright, guys, so let's move on to the last thing for today. That is the two most famous application of hashing. Is known as the hash map and hash set and the hash map. The hash set, this term is for Java users, and the unordered set is for CPP users. Basically, if you are a user from C++ community, then you are probably familiar with this, more familiar with this term, unordered set. And for Java users, it's hash set basically. So whatever we have discussed so far is basically an application of hash set. A hash set is something which what is a set? A set is basically, we are taught in elementary mathematics that a set is something which has very distinct elements. That is, you don't have repetitions. Like you can have 1 5 or 1 6. You don't have 2 6s or something like that. So a hash set is something which is a collection of distinct elements, and it helps us perform lookup, add, and delete queries in an amortized complexity of O of 1. Similarly, there is another application of hashing in which is known as the hash map, and for C++ users it is known as the unordered map. So what does hash map do? Hash map basically helps us hold mapping relationships. That is, it helps us hold a key value pair. For example, cities and their capitals. So for example, I want to create a data structure. I want to somehow store capitals and their cities. So like I want to store some cities and their corresponding capitals. So something like that. So if we have to do that, we need something called hash map. So what is hash map do? Hash map takes the key and it hashes it. So it hashes the key. It hashes the key and stores the value and stores the corresponding value. So hash map and hash set are the two most famous application of unordered set. It's useful for accessing elements by specifying their key. So you can just specify their key. So for example, if I want to find out the capital of some city, I will just have to provide the API the key, and it will just pop out the value. And it performs lookup, add, delete queries in amortized complexity of O of 1. So that is all about hash map and hash set. So next session we are going to do some of this base. So we're going to do some basic questions which will be based on this hash set and hash map. So guys who would be attending the next session, I would request you guys to just go through the documentation of this stuffs and just take a look at how things work. And if you have any more questions now, you're free to ask me. Okay guys, so if you don't have any more questions for me, then let's end the session here today. I had a lot of fun teaching you guys, hoping for more such sessions in the future. Thank you for joining. Bye guys.